Hello, nice to meet you. I'm Philip Benna. I work at Codasip as a product manager of the Codasip Studio tool, which is one of the demos you can see today at Embedded World. And I'm going to show you a quick walkthrough for some of the standard actions and workflows that you can do in Codasip Studio. So, just a quick introduction to Codasip Studio. Codasip Studio is an EDA tool that generates from a single processor code description in a language called Codal number of outputs. Today I will focus mostly on the software development tools that we can generate, but we can also generate RTL, we can generate UVM environments and other bits which are more hardware related. As you can see, I have a number of these Codal projects in my Codasip Studio instance today, and I will use them throughout the demo. The thing that I wanted to show first is the software tools that we're able to generate from Codasip Studio. So as you can see here, all of these little arrows or play buttons represent different tasks that are tools that Studio can generate for you automatically. Here under SDK, you can see that we can generate everything from assembler through LLVM-based C and C++ compiler to debugger, linker, and different types of simulators which simulate your code with a different precision and a different speed. All of that wouldn't make a lot of sense if we couldn't modify our processors, right? So the whole point is that you can modify the processor on your own machine, and you can then go and generate these tools again on your own machine. So let's look at some of the modifications that you can do with Codasip Studio. The first type of modifications I'm going to show to you is the simplest one, which is a configuration. So I'm going to open this file, and what you can see is a graphical environment which shows you the configuration options that would normally come with one of our processors. And you can see that there are certain instruction set extensions that you can enable and disable. There are some custom DSP instructions that Codasip has already designed and verified for you. So you can simply enable them, and you can go ahead and generate all the software tools, and they will already work with the selection of the instructions that you made. As I mentioned, this is the simplest type of modification that you can do to our processors because it doesn't really require you to design anything. But at the same time, you have to rely on the options that Codasip already provided, although there are quite a few of them in every of our processors. What I want to show you today is that you can also modify the processor in a way that you will add custom instructions that are fitting your specific application. I'm going to use a very, very simple algorithm to demonstrate it so that the demo is clear. But later on, I'm going to show you that it works perfectly for much more complicated programs as well. So I'm going to open this FIR application. And you see that this is a simple C algorithm, which is doing the multiply accumulate operation in a loop. What I'm going to do, actually, I've done it before starting this demo so that you don't have to wait a minute for the tools to generate. I'm going to run a profiling session to understand where the bottlenecks of this software application are. For a simple application like this, you would probably be able to figure this out just by looking at the code. But for the sake of the demo, I want to show you what our tools can do for you. So I'm going to open the profiling report that I obtained for this application using a baseline RISC-V processor. And what you can see is that from our profiling tools, you will get a report like this, which is showing lots of very useful information. The one that I would like to focus on is which function in this C application that I showed you is the code spending the most time in when executing. It's not a big surprise, but most of the time is spent in the FIR function. So this is the one where obviously your optimizations would probably pay the best. If you want to go further and you want to understand what are the types of optimizations that you can do, you can take number of routes. You might go and examine the raw assembly that you can obviously get from our tools. But at the same time, you can again rely on the profiling report that we provided, and you can see some of the more advanced information that we provide. One of those is, for instance, the common sequences of instructions. So what I can show you is that I will look for the most common sequences of two instructions, and the ones which have some of the operands highlighted have an operand dependency between them. These are typically a very good candidates for instruction fusion, which will give you typically a performance boost, and at the same time, it will lower your code size. So what you can see here is that the most common instruction pair where there is a dependency between the operands is load and addition coming after it, and the second one is multiplication and addition. If I go back to the C code, the reason for it is because the core of the loop is executing multiply accumulate, so multiplication addition, and every iteration of the loop I'm accessing a certain elements of this array and I'm incrementing the pointers to the array, so that's the load and addition. What I already have prepared before the demo is a version of the processor that I have used to obtain these profiling reports, which is also adding some custom instructions. So let's have a look at that. I'm going to open the relevant Codal file, which is describing the custom instructions that are optimizing this example application that I showed you. Let me make some room here. All right, so let's focus on this piece of code. As you can see, in a couple of lines, just this block of code, I have defined a custom instruction which is doing a multiplication and addition in one instruction. Obviously, this is a simple example, as I said, but it's very clearly demonstrating what our tools can do. You can see that the definition of the instruction looks pretty much like the C code. The core of it is the semantic of the algorithmic operation that the instruction is doing. And as you can see, the definition of this algorithmic operation, which is doing multiplication and addition in one instruction, is kind of similar to a C code that you would normally write. The reason I'm stressing this is that being able to define instructions on this level means that even as a software developer, you are able to prototype new custom instructions into our processors using Codal and Studio, and the only thing you have to know is essentially how you would describe them in C. There is nothing complicated about that. So let's assume that I already have a processor with these custom instructions, which I have prepared. The other custom instructions that I have here is also an instruction which is loading a data from memory and incrementing the pointer to the memory in one go, which was the other common pattern that I showed you in the profiling report. So what I'm going to show you now is the effect that custom instructions can have on this simple application that I was using throughout the demo. I'm going to use another view for this that I haven't shown you before, which is the profiling view. In the profiling view, I have two profiles. One is from the original SDK that doesn't have any custom instructions. And the second one is the SDK, which already is implementing the two custom instructions that I showed you. So the one for multiply and accumulate, and the one for load post increment. So let me open both of the profiling report at the same time. And what this profiling report will show you is that the profiler identified, let's say, two blocks of code in my for loop. One is, let's say, implementing the for loop itself, and one of them is implementing the multiply accumulate operation. The part that I would focus on is the number of instructions that are needed to execute these pieces of code. So you can see that the original SDK requires more than 7,000 instructions for both of these parts. The second column here is what the optimized SDK requires. And you can see that we were able to get from 7,000 instructions for the first block to over 3,000, and from 7,000 for the second block to less than 6,000. So you can quickly glance and see that my optimizations are already paying off on this application. Obviously, the overall effect will depend on the entire application, and the more complex the application, the more complex the custom instructions are, the better effect you will probably see. What I can quickly show you is such more complicated algorithm, because as I mentioned, this one is relatively simple. The other one that I have here is the SHA-500 algorithm. I have already the profiling reports for the version which doesn't use any custom instructions, and a version which is using a custom instructions that we have implemented. So let me open both and just quickly show you the benefits that you can get on a real-life application like this. So if I open the unoptimized one, you can see that the function which is used the most in this example is a function actually executing this encryption algorithm. And you can see that the entire function took almost 140,000 cycles. I already prepared an optimized version of it. I'm going to open the profiling report for the optimized one. And what you can see here is that the number of cycles dropped to less than 60,000. So we are now running the same algorithm using custom instructions for less than half of the cycles. The last bit that I would like to show you is the capability of Codasip Studio to also generate RTL from the same description that I have used to design the instruction and then generate the SDK from it. So if I go to the task menu, I'm gonna use the same model that I used, which was implementing the Mac instruction, and I'm gonna hit this button and generate RTL, which is a very quick task. It only takes a couple of seconds. What I can show you then on such generated RTL are two things. So let me just open the right generated RTL file. So I'm going to open this one. And to explain what I would like to show you is I'm going to open again the code description. So what I can show you here is that here is the file that I already used in the previous parts of demo, which is implementing the Mac instruction. If I find the same Mac instruction in the generated RTL, which will take me a little bit of time. Here we go. I can show you that essentially every line of the generated RTL is annotated with links back to the codal code. So you can see that, for instance, this line of RTL is implementing this code, and it is here in the generated RTL because we have wrote this line of codal. That is really useful because if you're working with generated RTL and you're trying to debug it, it's very important that you understand where in the higher level description language have you potentially done something that caused the generator to generate exactly this RTL. This is essential for working with languages and tools like Studio. And so we make sure that it's very easy for you to find the codal code that made your RTL look the way it does. The second thing I would like to show, and that's the last thing in this demo on the generated RTL, is that designing the processor in Codal is actually simplifying the design of processor and at the same time making the customization easier. So what I'm going to show you is that you probably remember that from the earlier parts of demo, but the whole description of the instruction is broken into groups of operations that are assigned to a certain stage in the processor pipeline. So you can see that the main arithmetic operation is happening in the execute stage. And for instance, the operands are read from the registers in the ID stage. However, there are no control signals, no pipeline registers which would hold the values that need to be passed between these stages. You can see, on the other hand, that in the generated RTL, we have all of these signals, right? And this is the abstraction that we provide through Codasip Studio, where you don't really have to focus on these low-level details. Studio will generate all of this for you. And if you decide to modify your implementation, if you decide to break the implementation of the instruction into more stages, you just have to change all of these annotations, and Studio will generate the control signals and registers automatically for you. Obviously, some of the implementation that I showed you is simplified, which means that some of the signals can be shared between multiple instructions, which is what we would normally do in our production code. But for the purpose of the demo, I wanted to clearly demonstrate that there are certain signals that Studio generated because I added this custom instruction here, and I didn't have to do this manually.